So myself, Sabyasachi, and I'm going to talk about AMASE project, stands for Affordable Multiple Aperture Spectroscopy Explorer. In Zulu, it's AMASE. I don't say spoiled, it's just shower milk or something. So if you look at the small notes on the small fonts on the bottom, we are covering almost all the BRICS members except for Brazil. So we are looking for partners who would want to join, would interested through this platform. But it's just not people from Brazil, any university and institutes in any of the BRICS countries. If you feel excited about what I'm going to talk, please reach out. So what's the core of core science that we are trying to achieve? It's something beyond H1, H2. So what's the efficiency of star formation in different galaxies? So what we are plotting here is the mass function. For example, the continuous black one is the mass function for the dark matter halos. And if you use the lambda CDM model, divided it by 5, get the baryonic mass function. And then if you plot the stellar mass function, that's how much stars are in there. And then you see a huge discrepancy. So yes, Milky Way sits very near to the knee of the curve, which is very close to the baryonic mass function. But if you go and look for higher mass galaxies or lower mass galaxies, the star formation is really inefficient. Why is that? We don't know. And so the idea with AMASE is that AMASE is going to look at 3 orders of magnitude in galaxy mass to try and understand how this process of star formation affects in lower mass galaxies, especially nearby universe where we can actually resolve the star forming regions. So one of the ways to probe the star formation is looking at the star formation feedback. And by feedback, we generally look at emission line maps in a BPT diagram. A BPT diagram is basically X and Y, where both have ratios of emission lines against nearby Balmer lines. So for example, N2 over H alpha, N2S2 or oxygen 1 over H alpha, or if it is oxygen 3, then it's H beta. And the strength of these lines, the ratio basically tells us whether they are falling in regions where there's star forming, like H2-like regions, or is it Aegean, like strong emission lines, or is it somewhere in between composite or like a low intensity emission region we call Lyre. And then if you use different emission line characteristics, you'd see that they are quite different. And if you use the existing photoionization models, they don't match each other. So the cyan curves, the cyan mesh-like grid, is basically the photoionization model overplotted on each of these 3, nitrogen, sulfur, and oxygen 1. And they don't agree to each other, and we don't know why. And basically the reason for that is that probably we don't understand the physics of H2 regions well enough, how it is working. So the plot I have produced here is from GN Yan 2020, and they're looking at manga data, which has a spatial resolution of about, I would say, a kiloparsec to 2 kiloparsec. And within that, there could be several, at least 2 to 3 star-forming regions. And even within each star-forming region, there are several molecular clouds, some giant molecular clouds. And unless we probe those in those small spatial resolution, we cannot understand what's going on in individual star-forming regions. So we really need to spatially resolve individual star-forming region well, very spatially well. And in addition to spatial resolution, we need to understand how they're varying spectrally. So people have already predicted that neutral atoms and ionized gas behaves differently under different influences. So for example, if it is neutral atom, neutral gas, then the radiation pressure is the sole dominator. And then they actually have, about 10 kilometer or so velocity. Whereas if you have ionized gas, then both radiation pressure and photoionization dominates. And then it just not only dominate at every location, For example, H-alpha H-alpha emission gases, H-alpha gas would probably be closer to the star-forming region, whereas the nitrogen-2 or sulfur-2 are probably towards the outer side of that star-forming region. So they have different velocity component, different affected area, different effective mechanism. So we basically need to go below that 10 kilometer per second velocity resolution, and we need about 15,000 resolution in H-alpha wavelengths. So where is the challenge? The challenge is we want to probe part of the star-forming region, but we can't do it within the existing instrument. If you go for instruments which look at outer extragalactic objects, then we really got down 1 arcsecond becomes 170 parsecs or odd, which are really, really big. If you're looking at galactic targets, then it's like 1,000th of a parsec, so we really don't need that kind of dynamic range, which means that overall area over your spatial resolution. So we need something in between, and that's what we need to do. And on top of that, what we need to do is contiguously map a region instead of looking at the usual context-wise, people do is a slit spectroscopy. So you put the object in your slit and take the spectra, but instead what we need is a 2D understanding of whatever we are doing, taking the spectra, putting in the BPT diagram and trying to understand the physics behind it. So we want to do it in 0.1 parsec or similar resolution because we want to sample each star-forming region, and then we need to go fairly high spectral resolution of 15,000 or about 8.5 to 9 kilometers per second. So this is what we want to do in nearby H2 regions. Now, if you scale that same, not spatial resolution, but the same spatial resolution converts to angular resolution in other parts, other H2 regions of Milky Way, then you can actually cover 0.1 parsec to 100 parsec. In LMC and SMC, you can actually using 10 parsec, you'll get 50 kiloparsec, and then 100 parsec at M31, the Andromeda and M33. So if you talk about dynamic range, you require 100 parsec, observing a contiguous chunk of 100 parsec at a resolution of 0.1 parsec. That's like 1,000 dynamic range. And the state-of-the-art telescope instrument combination is VLT Muse, and that has only 24 spectrographs. It has a dynamic range of 120, and that's the most complex spectrograph in optical we can talk about. So we basically need a lot of spectrographs, and the spectrographs are the most cost-driving factor in today's optical instrumentation. So we need to bring down the cost of the spectrographs really, really low. The fun bit about is that we don't really need big telescopes. So we are talking about 0.1 parsec in Milky Way, and that's about half an arcminute. So if you can really do it if we need to achieve that half arcminute spatial resolution, we are talking about a 50 to 30 centimeter fast telescope. It basically, it can be a DSLR lens that we use in front of our DSLR cameras. So that's how a telescope should be, instead of a really big, hunky option. And that's what we are trying to do. We are trying to bring down the cost of the spectrograph using off-the-shelf optical components. Like we are using a Nikon f.95 lens as the camera optics, where you're going to use very small fibers, 50 micron fiber to each sample spatially resolve the structure in the sky. So that is about 26 arcsecond. And then there will be 547 of them in individual, 547 fibers we're going to feed an individual spectrograph. We'll have blue and red channel looking at very specific part of the optical wavelength range, where we have the emission lines. Those are which cover the H-alpha and H-beta and surrounding regions. And we'll have a blue and red channel so that we can cover both them simultaneously. And if everything goes well, that's when we would get each and every spectrograph would cost about $150,000. That's like about 1/10 of the standard DESI spectrograph, which people are using for other For the telescope, yes, as I said, the telescope is basically a Canon lens, as a 400 millimeter f2.8 lens. But the fact that we're putting 547 fibers behind it is going to actually cover 79 square arc minutes. So it's going to be a really big footprint on sky. So how does the capability look like? So in our prototype phase, we will have 3 spectrographs in each hemisphere, 3 in Sutherland in South Africa, and 3 in China. So with 3 spectrographs, we can cover the Rosette Nebula in just 7 pointings, and that's about 2.2 square degree in area. So that's how fast it's going to be. If you benchmark it against the current available instrumentation, we are very, very high in terms of spectral resolution, very similar to cosmic wave imager or PPAC. And in terms of spatial resolution or spatial coverage, I think we will become the best, even beyond the current best SDSS-5 local volume mapper. So how far are we in terms of cost effectiveness? We are twice as cost effective as the current standard DAISY spectrograph. We have 4 to 5 times higher spectral resolution, but that comes as a shorter bandpass, about 20% of the DAISY bandpass. That's normal. And the idea is that the first prototype will come and operating in 2025, and we will cover about 300 square degrees with 6 telescope, 3 in north and 3 in south hemisphere. And the idea is that if we can demonstrate that how good the data is, how well we can observe within those 300 square degrees, we can actually, with 100 spectrographs in each hemisphere, we can actually cover a quarter of the sky in just 4 to 5 years. And we can actually, so the prototype is going to go down to 10 Raleigh, somewhere here, but the main survey can go up to 1 Raleigh. So that's just really faint. How far are we currently? So the optical design, optomechanical design, both are ready. We are trying to do most of the assembly right now because most of the components we are buying is off the shelf. So we have the telescope site ready at the South Africa. The search for the north side is still ongoing. We'll sort that out very soon. But however, the telescope, which will hold the Canon lens, and that Canon lens itself are being procured. The spectrographs, the detectors are procured, cameras are procured because they're all off the shelf. We have got our collimator and dichroic, everything in hand. So the only critical thing for spectrograph development is the grating, and that is being delivered in end of 2024, and that's what's setting us to get on sky in 2024. Otherwise, we would be much, much earlier. And then there's a fiber system that actually provided the 2D area on sky, and that's currently being developed meanwhile. So we are almost ready to actually start assembly. And with that, I would just like to stop, and here's your prototype summary, what all it thinks it can do. And if you're interested, if you want to look at what AMASE sciences are going to do, I just gave you a very quick overview of some of the key sciences, but there are several science goals that we want to achieve, including ionization, including mass metallicity relation, etc. You can just scan that and you can just have a look at it. Thank you.